Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host, Pedro Abreu, and in today's episode, we talk with Fabrizio Montesi, a full professor at the University of South Denmark. He is the creator of the Jolie Programming Language. He's the president of the Microservices Community and author of the book Choreographic Programming. In today's episode, we talk about the formal side of distributed systems. We talk about the calculi that model distributed systems, their type systems, their Corey-Howard correspondences, and all the main ideas around these concepts. But before we get into this conversation, which is really good, let's get into some messages for you guys. Here at Type Theory for All, we have a mission with open access and open education. We abhor the possibility of getting our content locked behind some kind of paywall. So in order to help us to deliver to you the best of type theory, programming languages, and formal methods for free, we humbly request your support through Ko-Fi. Simply go to our website, typetheoryforall.com, and follow the prompts. A donation of any amount, even $5, will be of a great assistance to our cause. Also, don't forget to follow us on Twitter at TT4All and joining our Discord. We're currently organizing a weekly study group to learn Calc through software foundations. So if you think that's something you'd be interested in, go to the website and join Discord today. This podcast is made possible thanks to our great sponsors, Formoland. Formoland is a formal verification company focused on verifying the implementation of programs in the Cockproof Assistant. They have been working in the verification of Rust and OCaml code for the blockchain industry, in particular for Thesis and Aleph Zero. So if you're looking to ensure an extra layer of correctness to your program, you should look into Formoland's work. All right, welcome everyone to one more episode of the Type Theory for All podcast. As always, is your host, Pedro Abreu, and today with me, I have our co-host, Dan Plukin. How are you doing, Dan?
I'm doing fine, Pedro Abreu. I'm glad to be back every single time. It's wonderful.
Look at us. We're almost professionals in speaking each other's name at this point, huh? Listen, dude, I heard that you moved places now. You're down south of the US now. What's going on with your life, man?
Oh, yeah. So I'm in Austin now. So I work. My joke is that I work for the University of Southern Denmark in Austin, Texas. And it's roasting here. It's going to be 106 degrees this week, which Fahrenheit. In Celsius, that's 41 degrees Celsius.
Holy
My parents
shit.
in New Hampshire think that like I've just been incinerated, but it's like a different vibe. Yeah.
But talking about Denmark, we're gonna meet your. How do you say when you're a postdoc? You don't call the guy you work with your advisor anymore. What's the proper title here?
I call him boss.
Boss. So today we have Dan's boss, Fabrizio Montesi. How are you doing, man?
Yeah, hey Pedro, I'm doing fine, and thanks for inviting me. Thanks, Dan, as well. Hi there. It's great to be here.
How's the weather in Denmark? Is it also roasting over there?
It's fantastically sunny today.
Yeah.
Yeah, perfect for playing football. Instead, I'm here doing this podcast.
Oh no! Listen, I also heard that you have actually started your career kind of like a game developer. What's your story over there?
Oh, that brings me back. Let me see. I think the correct way of saying how I started out computer programming is by being my brother's right shoulder, because he's older than me, and I was always watching, looking from behind over his shoulder what he was programming at the time. I started doing, software for small companies that manage the simple databases and then growing into websites. But at some point, I think I was around 16, 15. I was a teenager. I joined an open source development group that was developing a server emulator for a massive multiplayer online role-playing game. I think that's how it goes.
MMORPGs.
MMORPG, exactly. It was, at the time, the biggest RPG that almost everybody was playing. And it was very popular to have these little server emulators.
Which one was it? Was it World of Warcraft?
No, it was Ultima Online. It was the one before.
Okay, yes, I heard of that one.
And I think I learned it was an invaluable learning experience. I remember, I think I was actually even younger because I never remember as a little teenager, I was interacting with all these people all over the world. And one of them turned out to be, I think, a family man. So he was basically in his 40s from the Netherlands, and he was so knowledgeable, and he helped us so much getting to know how to code an advanced server, a highly efficient server for a massive online game in C++. And then at some point, I ended up being the maintainer of the software, and we had a lot of users. So it was very exciting for me. I think I learned a lot of stuff that then turned out to be so valuable at the university, because when I got in love with the theory of programming, I was the guy with the examples. I knew a lot
Ah,
about what people were doing in practice, right? So
yeah.
that attracted a lot of collaborators, or at least it kind of, let's say, motivated them enough to suffer the collaborations with me, right? Because I was somehow useful at the time.
So
So
I
that's how we started.
It occurs to me that a lot of our listeners are undergrads and they probably got started programming with Minecraft, like writing Minecraft servers or Minecraft plugins. I'd be interested to hear how many people got started with that of our listener base. It might be like a depressing number in terms of how old Pedro and I are.
yes. But I've heard there was a guy that came here in the podcast before that he said that he started doing mods for Grand Theft Auto. Like you have to also write some scripts and do that kind of. That sounds so fun, honestly. Like just hacking the games, the internals. But so what you were doing there with Ultima Online was actually developing and maintaining the server, like the main code of
Yeah,
the
so
original
we
server.
basically became experts in reverse engineering the original protocol they developed, and we implemented the server basically from
Wow.
scratch at some point. Initially, we were building on another open source project. There was a very active community, and then I learned how to
Right.
reverse engineer it all. So it was a lot about, it was a huge event loop, which is what most software is today anyway on the internet, reacting to this very low
Right.
level protocol, sending a lot of events from all the clients and managing all these events. You needed to have a coherent picture and keep a coherent picture of the global state at all times. And I remember it was very exciting to manage the coordination between receiving these events, interacting with the persistent state, because this could crash, and then you wanted to recover gracefully from a crash. Otherwise, you would have very angry
Right.
players coming at you. Imagine you finally reached level 100, and now
Yes.
the server crashes and it forgets, right? So it was very important to manage persistency, which got me
Oh
interested into
God.
transactions. And it was very important to support plugins, because I was developing the core thing, and then the users would customize it. That's why these service simulators made sense, because it allowed these users to customize, and they were making their own versions of the game. Some were using it for real role playing in a sense. Some were using it in a completely different way, and they were inventing, new weapons, new character classes, all the jazz. And I had to learn how to integrate Lua and Perl interpreters into these C++ servers. So I had to learn foreign function interfaces and all that stuff. It was really, really exciting. It was like a gold mine of new things to learn every time I looked into something.
That is so fun. That is so cool. I have played an MMO for a long time too. It was Lineage 2. I don't know if you heard of that one. Lineage 2. And I also at some point I decided to use one of these servers, public servers, and then open up things and run your own server and have your own database. There's so much cool stuff that you can do there. And I remember in the end of the day, I was just running the server on my own machine, and nobody could join. It would just like be extremely glitchy. But I definitely relate with what you're saying. It's so much fun and actually seeing things running in a very precise way. But I'm curious, how did you go from that into like would you say that the core of your research is more in distributed
Yeah.
systems?
Uh, Almost everybody disagrees about what the core of my research is, because of reasons that might or might not become clear during this episode. But I basically joined the university. I started university at the University of Bologna, And my initial intention was to just get a bachelor's degree and get out of there. I wanted to understand more about programming, get a certification, a degree, and then go out and work again, because I already had part-time jobs in programming. When I reached, it was going very well, and I started loving the math courses. And at some point, I encountered a course on programming languages. And they were really advertising the fact, one of the co-teachers, a PhD student at the time, Claudio Guidi, was advertising the fact that they were offering the hardest possible thesis topic at that campus. It was the campus of Cesena, which is one of the campuses of University of Bologna. And so I started following this course. The course was really dense and packed. You had to learn how to build parsers, lots of parsing algorithms, how to do, how to make interpreters, all the way. This was the practical track of a basically compiler's course. And on the side, the other half of the course was basically complexity and computability. All of this fused in one huge course. So it was a lot of work with a huge project. Yeah, and a lot of theory.
That's hard.
I loved all of it, so I got a C. I got a C because I obviously I got in love with a part of the course, and I started completely neglecting another huge part of the course. And then they allowed me to take it again, because I discovered I loved it, and I didn't want to have a C. I think I then got a B, and then I took it again, and I finally got an A plus.
Oh wow! I got 2 times.
when I got the A plus and I showed my project, the two co-teachers. So the teacher was Gianluigi Davataro, fantastic guy at the University of Bologna, and I think Roberto Guerrieri was also involved. These are process calculi people, really concurrency theory people. And the co-teachers, the instructors, if you like, were Claudio Guidi, who was taking his PhD, and one of his postdoc colleagues, whose name is going to pop up to my mind later on, probably. But I interacted with Claudio a lot. And they were looking at my project at some point, where I made what I called an object-oriented interpreter, where each object represented a part of the program that could interpret its own meaning, in a sense, through polymorphism. And they asked me, where did you copy paste this from somewhere on the internet? And then we were like, yeah, maybe I should do a thesis here. From that thesis, we made the Jolie Programming Language. So that's how Jolie was born, in a sense. And I discovered I loved research. And then the plan was not to get a bachelor's degree anymore. It was to get a master's degree afterwards. And then the rest is history, as people say.
So that's interesting, because I thought the Jolie programming language, you guys started from this angle of like process calculi, and you want to make a language based on that. But actually, it came from just this organic meta interpreter object thing, used. And then the calculi came later.
But you are quite right, actually. That's how Jolie came to be. So Claudio, at the time, was taking his PhD in service-oriented computing, and he was using process calculi to study the theory of service-oriented architectures. This is like web services. I'm talking about these XML-based language specifications for describing the APIs of web services. XML was used as the de facto standard for message representation and serialization at the time and stuff like that. Early 2000s. There was a lot of money invested in research at the time. And Claudio was taking his PhD, and he had this idea of trying to use process calculi to model a bit more simply these big languages. So he was looking at the specification of these big languages made by big committees and tried to gather the essence of them using process calculi. Why did he use process calculi? Well, it probably because it was the University of Bologna, at the time and still today. They have one of the strongest set of people ever doing concurrency theory, because Davide San Giorgi is there, and Gianluigi Davataro is there, Roberto Guerrieri is there. There are many other people like Ugo Dallago, and really Cosimo Laneve, Ivan Lanese now. I'm saying the names of lots of Italians, but trust me, in case you don't know these people, you can DPLP them. That's slang for Google DPLP and then the name of the person. And you will find a series of amazing papers, right? And it was such a good match. Process calculi were such a good match to understand the semantics of service-oriented computing, because it's all about these services, which you can represent as replicated processes or recursive processes, essentially, that send and receive messages to each other. So at the time I arrived, and Claudio had this, prototype process calculus to model service-oriented computing a bit. And I thought, wow, these process calculi, I was interested in particular in the pi calculus at the time. They are really intuitive to me to understand, which probably means that my mind is completely broken, I think, because most people don't find them as the easiest entry point in theory of programming languages, but I understood pi calculus before I got into lambda calculus, which is kind of weird. Yeah, Dan is making, for the people who cannot see, everybody listening to this podcast, Dan was a mix of, disgust and surprise, I would say, mind-blown emoji right now. So, that's the story. When I saw the process calculus that Claudio was making, and Claudio and the others, they wanted to try and make a programming language out of that. I had an idea for how to implement it. I made part of the syntax my own, but I think it's very fair to say that Claudio and I basically co-created Jolie. It was his idea to try process calculi and made the first draft. Then I basically insert a lot of these primitives that we call for architectural programming, for composing services and creating services and defining their access points and so on and so forth. And it was a fantastic experience. And I think that Jolie is actually a bit of a success story in showing the usefulness of process calculi, even though it's still a very niche language. But it does simplify a lot of programming when you deal with that domain.
So I think maybe to back up and give people some context. I mean, when I was in my undergrad and even in grad school in the States, we didn't cover process calculi at all. And I'd never heard the term service-oriented computing until you were already my boss. So maybe so what's the whole motivation of service-oriented computing? Is it synonymous with microservices, which is another thing that people have heard of and probably don't know what it is? Like what's kind of the motivation behind that?
Right.
Why isn't one computer
enough? So there are
enough?
two parts to my question.
So
First is that I want to publicly declare that I did never ask Dan to call me boss. The second is that service-oriented computing is the precursor of microservices. So at the time, people were really interested in integrating software made at different organizations. I'm not a historian on this, but I would bet some small amount of money on this, maybe. And that's why they started inventing all of these standards to have technology agnostic representations of messages and APIs and so on and so forth, such that you could stop caring about in which language you have implemented stuff. You can always integrate whatever you have made by following these standards with everything else. Microservices happened later, I would say at least 10 years later, because service-oriented computing got really big in the early 2000s. And the microservices got really big in the early 2010, I think, something like that. A lot of people, including us, were, in a sense, already doing microservices in 2004, 2006. Indeed, I mean, we rebranded, when the term microservices came out, we rebranded Jolie as a microservices programming language, right? Because Jolie...
like everybody spinning everything as AI when it was actually just, a search algorithm or something.
I think many people miss why it has been valuable to switch to the term microservices. And part of it is that service-oriented computing connected to XML and these big design by committee languages and specifications, sometimes it was just slow, either at runtime or to adopt and understand, because to express one single operation signature, you had to write 10 lines of XML, which was not exactly intuitive to most. So the term microservices introduced a break, in a sense, from the old, slow and complicated concepts and technologies to what is lean and new. The concepts are exactly the same otherwise, right? But I think I can see at least that why it was somewhat necessary to rebrand the paradigm in a sense. Another thing that most people underestimate is the link to software architecture, design, and software engineering. Microservices are strongly designed to be within business boundaries. There's a strong link to domain-driven design. So you want to design your service to be small. But what does small even mean, right? In object-oriented computing, we say objects or classes should be small enough. They shouldn't be bigger than needed. Otherwise, you're making your code a mess. But what does small mean? And nobody knows. We talk about this at least every conference on microservices every year. And in this case, however, microservices, you can think of them as like a unit that implements an API centered around some business capabilities. So if there's an accounting department, they should manage their own microservices regarding accounting, for example. And then if there's another department responsible for managing the movie catalog, now I'm bringing up Netflix because it's always the coolest example people usually think of because they're kind of good at doing microservices, then they should manage the services for the movie catalog. And when you try to integrate these services, you should figure out what kind of data transfer objects you can have between them, what kind of universal language you can build across the organization. And this has been so useful at devising how you can organize the development of these microservices. In service-centered computing, it was often the case that people would make a huge service for the entire organization and just publish the entire API to the other organizations. And that's not what we do anymore. Now we modularize this, right? So I think this is also a very useful break from the old service-centered computing to the new microservices. And now I could mention another 1,000 things. But since we are at the Type Theory for All podcast, if people want to learn something new, I really recommend you Google Conway's Law if you're interested in how you should organize your microservices, because I think it's kind of revealing.
Should we explain? No, we'll just let them Google. What if they're like washing dishes or something like that? I'll summarize. Conway's law, I think, is the idea that your software architecture will mirror the organization, the way that your company is organized. So if you have an accounting department that is separate from the, I don't know, whatever other department there is, the quick, Fabrizio, give me a microservice.
Oh, you're doing fine by yourself, man. I see no problems.
The from the I don't know, there's a group that is responsible for like user accounts and one that is responsible for purchases. If you have those as separate groups, then your software architecture will have kind of a separate namespace for each of those two.
Yeah,
two
not only a namespace, but once you accept Conway's law, you should just bite the bullet and let the separate units at your organization develop independently these microservices. That's the idea, at least. Of course, you have to support them with the necessary technical know-how. So you switch from a model where you have a software development department to where maybe you can still have it, of course, but the software developers, they really need to get out. They need to get out to these teams and they need to learn their own languages, their own domain, and then they need to interact. And then that's where the software component called microservice is born, essentially. And then they need to get back and talk to the other people doing the microservices. They try, of course, and we should try always to keep it as loosely coupled as possible. But at the end of the day, some coupling is going to be there because these APIs need to be integrated in order to do something useful together, right? Because we're not in a monolith anymore. In the Jolie programming language, we actually take this to the extreme. In Jolie, one of the key interesting features of Jolie is that if you think about what is the component, the atomic component of reusable software, the concept of reusable component in Jolie, better put, is that of a service. We don't have objects, we don't have functions. You cannot write a function in Jolie. You cannot write an object, you can only write services. So now in order to make it an actually usable programming language, we had to figure out what it means for a service to have another service inside of it and to make it easy to have in-memory communication between services. And in theory of process calculi, we know that essentially a service is a generalization of what an object is, which is a generalization of what a function is, right? You can implement a function as an object that is stateless with a single method and no fields, in a sense. you can implement an object as a service where all methods are available at all times, which is not necessarily true in a service. Some methods might become available or disappear or not available at runtime.
So I also want to mention that I think one of the things that really sold the idea of microservices to me, I thought like, oh, why don't we just use objects and stuff and just put everything in? So you use the term monolith. A monolith, in case people aren't familiar, it's when you just have one big server that basically runs your entire code base. So you might have different objects that are responsible for, this one is responsible for the shopping cart, this one is responsible for the user account. And you would think that, okay, I'll just have like a really big beefy server that runs all this stuff. But one of the big motivations for decoupling these things as separate machines, even, or separate services, is because if one has a programming bug in it, like maybe it hits an infinite loop, there's a bad regex or something, then just that component of your application will fail, but the rest of the application will still work. So you can still see the Twitter timeline, but you won't be able to update your email preferences or something. So, and that translates to money in the bank, as I understand it. So with that kind of background, I think Jolie tries to make services as like first class objects that you can, with this looser coupling than objects, or that an object oriented programming that a monolith would have, that you can just program with these services that are all communicating by messages. And maybe this guy's not going to give you a message back. You send him a message and he's, processing a regex for however amount of time. And so Jolie, I guess it makes it easier to do that sort of thing. But it has like this process calculi background, which I guess maybe this is a good time to talk about like what is even a process calculus, because that was another thing that I never learned in my American education.
We certainly can. I would just like to make a comment maybe about these microservices.
Oh, sure.
Of course, what you said is true. One of the point of microservices is to avoid single point of failure, right? However, on the other hand, now every time you interact with another component, in this case services, and Jolie makes it very evident, every invocation might fail. And you have to deal with that, right? So that's something you don't have in a monolith. So developing a monolith is easier. And many people recommend even to make what they call, I think, a monolith that then you sacrifice later. I think it's a sacrificial architecture or something like that. Sacrificial architecture.
Sacrificial architecture?
Much. And Spring recently and others, they have introduced this concept of a modulith. It's a monolith that you try to keep as modular as possible with its own tests and separate from the other components of your monolith. What Jolie does here is that it actually forbids you at the language level to have shared memory across the components. So it helps you with that, with keeping stuff modular. It also helps you with deciding later on refactorings that are what I would call deployment refactorings. So if you have a service that's currently running inside of your bigger service, it's like a subcomponent, and you want to take it out later and make it distributed, you can always do that whenever you want, modulo some plumbing of the configuration files, right? But keeping the code separate by via the design of a programming language is what we want to do in essence. Otherwise, people could just make a framework in a sense. And then you ask, what is a process calculus? Am I right?
I did ask that. Although this whole time Pedro has been looking increasingly concerned. So I wonder if maybe we should take a break and make sure that the type theory people are still on board.
So the first thing that got me concerned is that my internet was glitchy, so I missed a little bit of the discussion. But that is not an issue at all because all the files are already in the backend, so I'm not too concerned about that. But let's hear a little bit. How would you define process calculus? How does it compare with the lambda calculus, which I think our listeners will be a little more familiar with? And then how does it lead to a good approach to microservices? And and then I have one other question when we reach back into microservice.
And I promise that this will get back to types in several points. I think.
I promise I will fulfill your promise then.
That was a good
So
joke.
let's see, what is a process calculus? So a process calculus is essentially a formal model for defining, well, actually, sorry, a process calculus is a meta model, arguably, like lambda calculus, for modeling concurrent systems. You can think of a process calculus as a language that you use to model a concurrent system. The people usually try to keep them quite simple, these process calculi. So you have very simple primitives for sending and receive messages, receiving messages. So you send over a channel some payload, or you receive over a channel on some local name X that then gets bound to the continuation. You replace it with the message payload. And then why are they called calculi? Some people even call them process algebras. And that's because in order to build complex terms or complex programs in these languages, you use algebraic operators or operators that have algebraic laws or are explained in these terms, like parallel composition. So you can put two processes. Processes are just names for terms in this context. So you can put two processes in parallel. This allows them to interact by using these send and receive primitives. You can compose them with a plus operator. That means you do either that, the first process, or the second process. You can use the replicated operator, which will bring us back to type theory later, which replication. So you write bang or exclamation mark, if you like, P, which means as many copies of P as you like. And then out of all of this, you surprisingly get, or maybe not surprisingly to some, we will see, a Turing complete language out of a very simple set of primitives. They are usually imperative. You just express a sequence of these actions, or you compose things in parallel. You can compose these two ways of building things. And I guess that's essentially what a process calculus is.
Mm-hmm. And how does that lead to microservices now?
Well, microservices are essentially processes that send and receive messages to and from each other, right?
So you've mentioned that microservices, in some sense, is a further layer of abstraction on of object-oriented programming. How do you come with that conclusion? It's not clear to me. What is the idea there?
So when you write, and maybe this is not something that every expert on microservices might say. This is my own personal take, coming from the merge of service-oriented computing and process calculi, right? However, process calculi have affected also these big languages that have been designed by committees. You can see that they were in strong contact with the concurrency theory community. So something you do with these languages for expressing the behavior of services is that you can write things like, first, I'm going to receive on this operation. Let's call it operation 1. And then I'm going to receive another message on operation 2, on two separate variables. Then you combine them and you send the message somewhere else. Okay. Now, this means that operation 2 is not available until you call operation 1. And that's something you don't have in objects. In objects, all methods are available at all time.
Mm-hmm.
It's the client that determines in which order they're called. Instead, when you write a service, the service, when you open a session with the service might determine that you must call the operations in a given order. And this is why we can connect to type theory.
Mm-hmm.
This is why session types are so damn interesting for this domain, essentially.
All right, let's get into
Session
that. What is
types
session types then?
are types for protocols, you might say. Say that you have
Okay.
a bunch of processes that now, and you wanna express in a sense how they're going to interact with each other. So when you write the program, you might say this program is going on this channel to send an integer and then receive a string. Then the session type that you type the behavior of this process on this channel with is send an integer and receive a string later. So it's a kind of like an abstract process. Actually, we know it is formally that there are works where they take this view literally and they type processes in a process calculus with the terms in a simpler, more abstract process calculus. And you can give a semantics to session types using exactly the same techniques that we use for process calculi. So process calculi are one fundamental part in the toolbox of session types. And the other part would be linear logic, which have been a tremendous inspiration for session types.
Okay, so yeah, I think linear logic. I don't know. Maybe the listeners, at least I am a little more familiar with, right? Like where you will use your variable once, you can call your function. You know exactly that you must do this exactly once or not. And what is the name? There is another theory that also you have a larger amount of time, that a larger amount of use that you can do, right? Like can use more than one time, but
No,
that's
that
not
would
linear
be, then
anymore,
you
is
have
it?
other logics like affine logic,
Right,
sub-exponentials, where you can
right.
put a number to how many times you're going to use some resources and things like that.
Right, exactly. So then session types will be an even further
No, that session
abstraction on top
types
of that.
are, if you take the real fundamental, the most simple, in a sense, take on session types, then it corresponds exactly to the propositions in linear logic. They are in a Curry-Howard correspondence. So they are exactly the same thing as linear propositions.
Ah,
And we
right.
know that the
Mm.
inference rules that you use to express a session type system are essentially the rules of linear logic. So I would say that linear logic, if you're looking
Ah,
for what does it correspond to, then session types and then you have the proofs in linear logic correspond to session type processes in a process calculus, which we know is the internal pi calculus. It's a particular variant of the pi calculus, well, a fragment, I would rather say. Then that's where we're at, and there's a fantastic stream of works starting from around 2010, since Kairesh and Fenning showed the correspondence in new terms. These were like the emperor's new clothes in a sense, because people had known that linear logic, since Abramsky and Bellin and Scott's early works, we knew that session types corresponded to interesting linear types for the pi calculus. But session types, and actually we also know that session types are kind of like a nice layer of abstraction on top of linear types for the pi calculus, because you can encode session types into simpler linear types for the pi calculus very easily. However, session types, I think, have been very successful because they're such an intuitive language. It's very easy to write things like send an integer, semicolon or dot, to express a sequence, receive a string. It's really, really easy. So people can immediately understand them and use them to write protocol specifications. And I think that's a big part of the secret of their success.
And one of the big reasons why you would want session types is to prevent like a new kind of bug that happens when you move from monoliths to microservices or to service-oriented computing, which is like deadlocks, or you send a message from one process to another, and that other process, well, like I send a hello message to Pedro, but Pedro is in a state where whenever he sees a hello, he does something unexpected, because he's maybe expecting a hello message from somebody else, but he gets a hello message from me, and then I don't know, then he says F off or something. So your session type will ensure that if I send a hello message to Pedro, he will send me back the thing that I expect, and that also neither one of us is going to get kind of stuck. So, Fabrizio, after you've said so much nice stuff about session types, why don't you tell us about how you've implemented session types for the Jolie programming language and why you were
I
so
haven't.
successful
That's the
in doing
secret.
so?
I did something else. I implemented another language, which is session types, and I compiled it to Jolie. Implementing session types for Jolie
ah,
is not that easy. That's because in Jolie is, and it might sound absurd, but Jolie is a technology agnostic technology. It assumes absolutely nothing about how you are implementing channels. It's all based on data. So basically, when you want to implement something like a channel, you have to tell Jolie which data inside of messages represents the unique piece of information that the interpreter of Jolie can use to distinguish if you're communicating on channel X or channel Y. The messages that come through these channels, they must have some data. Maybe it's some metadata, maybe it's some message header. but you must tell Jolie where it is such that it can distinguish those channels. And this is very general. This is what people use in service-oriented computing, and it was a necessity because some people, some organization might identify channels by writing something in the field session ID, and some other organization might say, oh, well, it's the pair of your social security number and an automatically generated ID, which is unique only for that social security number. You might have overlaps if you use the same ID with another social security number. Maybe it's another channel. So sometimes it's about the combination of data. And when you think about that, we are still working. We just recently made a theory together with Saverio Gianlorenzo on how you map session channels to this kind of information. But I really liked your example about how you and Pedro would communicate through session types then, because you have basically explained why these are linear types. If I say that I send an integer, I do it exactly once. And if I say that then I receive a string, I will do that exactly once. And any compatible process with this will have to receive an integer exactly once and send a string afterwards exactly once, which guarantees deadlock freedom if we have only this channel. If you have interleavings, you might still have deadlocks. And the fact, also very important, not to be underestimated, that you're actually implementing the protocol that you're promising, which might be a requirement in itself, that you are promising that your service follows this protocol because maybe it's a standard and you want to certify that it follows this standard, right? But I would also say that calling it an approach to microservices is also limiting. I think this you can use everywhere. You could use it in the kernel. You could use it for hardware. I mean, at the end of the day, a computer is just a bunch of components that are communicated by message passing. Shared memory is an abstraction we built on top of it, but really we are sending these messages over buses and reaching RAM components and caches and CPUs and whatnot. I wonder what all of this would look like if we started modeling it with process calculi and typing it with session types.
Yeah, that was like one of the biggest like mind blown moments is when I realized actually your computer, even by itself, is a distributed system.
Do you know
It's so
that they put
complex.
batteries
It's
inside of
fascinating.
SSDs? I once reviewed a
Really?
paper where they called me in. It was an operating systems conference. And I read this paper. It was super interesting about a new strategy for resilience in SSDs and solid state drives. And these solid
Right.
state drives, in order to be fast, because that's also their raison d'etre, right? They gotta be fast. They have a RAM module. So when you write something, you are writing it to the RAM module. And in order to be even faster, now when you f-sync on some of these drives, you have just written to the RAM. They just say, yeah, you have synced whatever. Now I'm not an expert. I don't remember if it was f-sync. But anyway, some of these drives, they just tell you, don't worry, it's persistent now. And it's not actually true. So what did they do? The geniuses, they are actually geniuses because they are selling a lot of drives, right? They put tiny batteries, apparently, that just in case the computer is cut off from electricity before they could commit the modifications in the RAM to the solid state, the battery just keeps it alive for a little while, hopefully for long enough.
Are you saying that
Oh
my hard
yeah, it's
drive is a
independently
microservice?
deployable. Let me look at the list of features. Too many to list now. I don't think battery powered is a necessity though for microservices.
That is incredible. That is so interesting. I mean, industry, they always come up with amazing ways to get our money, right? But that is a very very interesting idea. So if I understand correctly, so the idea that Jolie doesn't implement session types, and that would be pretty hard, is because you want to make it as agnostic as possible, technology agnostic as possible, and to be as general as possible. So that's a good reason for not even having a very strong type system. Is that
True.
correct?
Jolie is a bit weird in that sense because we don't type yet, although now we have just finished making an initial theory for a type system for Jolie that does not require type annotations. It just figures everything out from how you manipulate data. But Jolie is very strongly typed at the API level. It's one of the main features in a sense. So when we write what people call in software engineering the access points or the endpoints, these are the input and output ports. So an input port is where I can receive messages, and an output port is a dependency that I'm going to invoke the API of in order to be able to work. And these can be remote, right? These output ports. So you are contacting a potential external service. Now, basically, these ports, they have an API, and we write the type of these APIs. And usually we have primitives that really require this type information because, for example, there's a pattern in microservices called merge endpoints. You have two separate microservices, and now you want to offer the API of both, the union of their APIs, on a single endpoint, maybe an API gateway. Doing this usually takes one line of code because it's a primitive. It's called aggregation. So you can aggregate these output ports. And what this means is that now you have created a new input port that accepts calls for these conjoined APIs and then forwards it to the right service whenever it gets a request, essentially. And in order to forward the request correctly, I need to look at the operation that you're invoking, right? So type information is very important when we do what we call architectural programming in Jolie, where we have some new primitives, essentially. And when instead we program the internal behavior of a service, there it's a bit trickier because what we adopted there, and now maybe I'm shooting my own career here, is what I would call a purely mutable programming language. So in Jolie, there's basically all you're doing is you receive some messages potentially from multiple places, and then you mutate the data structures a bit, or you put them together in another data structure, and then you send it back. That's what most people do in microservices. Like at Netflix, you might have to compose the Netflix web page, and it displays the movies with their titles and the user ratings. And this might come from two separate microservices. So now you have to invoke them and then combine the data structures and then send them back as a single data structure. So all we do usually is mutating trees, essentially, JSON stuff that looks like JSON trees, a generalization of them. And what we are seeing now is that thanks to recent results, there's a line of work by Giuseppe Castagna and others on studying this kind of languages that we have recently extended. You can reason about it by having judgments that say, if you start from a state where the variables have these types, and then you run this instruction, now the state you get in, the variables have these other types, right? You have mutated them, which is very weird. We have variables that mutate types while you run your code. Yeah, because maybe you have a data tree weird. And you add a field, just like you do in JavaScript all the time, really. So people who try to type JavaScript, they have to support very similar features. You can even remove part of a tree, and now you have cut part of a type, you know?
To all the Haskell programmers currently having a heart attack while listening to this podcast, just pretend it's a monad that's purely functional. It's just linear transformation. So you take an input and then you produce an output and you throw away that old input. That's what mutation is.
It is actually, but it was on my bucket list to give a heart attack to some. This is just a joke. I hope nobody got a heart attack, but to scare a little bit some Haskell programmers. Thank you, Gary.
But so when I was talking about the surely you made a session type system for Jolie, I was actually trying to get at what you were trying to solve the problem of kind of how do I write implementations of my processes and get them to actually do what I meant them to. But you took a totally different approach from the session type approach, which is choreographic programming.
Well,
so maybe a good place to start is like, I mean, what was the state of choreographic programming when you came to see it? It kind of co-evolved with session types. I don't really understand its history too well.
Choreographic programming definitely evolved together with session types. At least there were important points where they came in touch. Also, it kind of developed mainly within the same community at some point, because we were interested really in the same thing, in making these processes behave as we wanted them to, right? Now, choreographic programming, I think the initial inspiration that choreographic programming wouldn't have been possible without is actually the Alice and Bob notation for security protocols, right? These A arrow B colon M, meaning Alice communicates to Bob the message M, that people still find in protocol design, essentially. That's where we got the syntax from, and that's the syntax that got adopted in both multi-party session types, which is essentially session types where you can have more than 2 participants. You can say Alice communicates to Bob an integer, and then Bob communicates to Carol a string, and then verify this, that they collectively behave like this. Or you can write a choreography, a choreographic program, I would rather say, because a choreography is a very broad term, right? So when I say choreography here, I mean a choreographic program, where you can write Alice communicates to Bob the number 5, or maybe Alice computes an expression that returns the number 5 and communicates the result to Bob. Then Bob communicates something that it computes from the number 5 to Carol. So you write the actual program of all participants from this overall viewpoint, this objective viewpoint, as we started calling it, or as many people called it and still call it, the global viewpoint of choreographic programming. Now, these are very similar languages. I mean, they both use this Alice arrow Bob notation, right?
Yeah. So if I understand correctly, like a session type or a multi-party session type is just the generalization of that. You write a type, and then the compiler will project that type into local types for each of your processes. And then you check that your process will obey that local type. Whereas a choreographic program it's a program that you write and you project it, and that gives you the process itself. Instead of giving you a type that you have to check the process matches, it gives you the actual process that's going to do all the work.
So you can think about it like this. Your aim is to implement a protocol, okay? Now, with session types, what you do is that you write a specification of the protocol. You have to abstract from computation, otherwise type checking is going to be hard. And then you compile it down to the local specification for each process. And now if each process respects this local specification, then collectively they all implement the protocol that you wrote as a multi-party session type at the top, in a sense. So this is basically verification, if you like, right? Choreographic programming is born of the consideration that if this is so important, if we are so interested in implementing these protocols, why don't we just make a high-level programming language for that? So imagine that if to you in these protocols, the key primitive is that of a communication, then instead of trying to verify that you are implementing that communication that you're interested in, why don't we make a programming language that has an abstraction for communication? And now you can just program with it, and you get a compiler that guarantees that the code you get out is a distributed application, essentially, that implements your choreography, the program you wrote by composing these communications. It's a bit, sometimes I think of it as by drawing a parallel with functional programming. So if you're so interested, if you think the programming with functions is a really good idea, then would you rather write code in a low-level language where you don't have function calls and definitions? You have something lower level. And now you need to verify that this piece of code is a function call, and this other piece of code is the definition of a function. And when you put them together, they do the function the application that you were actually thinking about, right? Many people today would say that that's totally crazy. Just use a language where you have syntax for writing functions and calling them. And I'm not saying that people are crazy for using the languages we have today, of course, but I think it's quite interesting to think about, all right, if we accept that communication is the key thing happening in a distributed system, or even in any communicating concurrent system, then we should do the same. We should build a language where communication is an abstraction. And then the interesting research topic becomes, what's its syntax, and what are the laws that this abstraction respects, right? how is it defined? And one of the when I started my PhD, which is when we developed a lot of choreographic programming, I did not have the intention of creating a paradigm at the time. I came to this realization towards the end of the PhD because we discovered a few things. And most importantly, we discovered these laws. We discovered that there are interesting laws that explain what the composition of different communications in a sequence, for example, actually means. So that was the breakthrough, in a sense. We also discovered that when you put, for example, two communications in sequence and they are independent, because maybe you wrote Alice communicates to Bob and then Carol communicates to, what's the D then? Name starting with a D? Dan.
Dan.
Dan. You just.
Hey, Pedro, at least I asked the right person, right? So anyway, so obviously the communication between Alice and Bob and then the communication between Carol and Dan, since they are separate participants, they are totally independent. So if you write a choreography like this, there are two independent communications that could happen in any order. So we discovered the law that if you write a communication followed by another communication between completely distinct participants, this is equivalent to the same choreography where the two communications are swapped, where first Carol sends to Dan and then Alice communicates to Bob. And this, in a fascinating way, since at the time people were studying the Carry-Howard correspondence between linear logic and the pi calculus, I was interested in studying the Carry-Howard, what choreographies correspond to in this framework. And we discovered that choreographies are syntactic descriptions of cut reductions in proof simplification in linear logic. They are exactly that. And this law where you can swap or run in any order communications that are independent in a choreography, it actually corresponds to the fact that some cut reductions can be performed concurrently in proof simplification in linear logic, that they are independent. And it's exactly the one and the same thing. And when I saw this, I started thinking that, okay, maybe this thing, it should be given a name, and it's a paradigm worth considering because it looks like it has a very deep foundation in what we already know. So I can even hope maybe to communicate what the heck it is to others in the future.
So this is an interesting point. Like you said that session types correspond already to linear logic, but there's also this correspondence between choreographies and linear logic. So what's the difference
Session
there?
types correspond to propositions in linear logic. So the formula that you're proving, essentially. Processes correspond to proofs in linear logic. When processes interact, so they communicate, each communication we know corresponds to a cut reduction in linear logic. If you look at the sequence in which you made these cut reductions, you get a choreography, one-to-one. So choreographies are a way to describe the process by which you have simplified the proof in linear logic. It's a syntax for cut elimination, if you like.
Uh-huh. But it's also a programming language for implementing kind of
Yes, because
distributed
we know that
applications.
once you know the cut reductions that you want to make, speaking still in linear logic terms, we can synthesize proofs that implement those cut reductions. So that's what compiling a choreography is under this interpretation, essentially. You tell me what kind of cut reductions you want to see because they correspond to communication. So that's what you're interested in. And I will synthesize for you the processes that will actually be simplified like this.
Mm-hmm. Interesting. But I want to back up and say, so did you coin the term choreographic programming? Did it exist before that? I think, like, if I look in the literature, choreographies have different meanings, and sometimes they behave a little bit like multi-party session types.
So
if I'm not mistaken.
I call a choreography just any coordination plan for a communicating system, essentially. So for me,
so session
yes,
types
what people
fall
call a
under that
global
umbrella.
type or these multi-party session types described in this Alice and Bob notation, right? So these are choreographies, in my view, if we are being general. A choreographic program is also choreography for me. It's just way more specific because it's computable in a sense. Well, it defines computations at the participant. So it's a real executable program. I think in the beginning, this created a lot of confusion because choreography before multi-party session types and choreographic programming, it meant for some just the idea of having a decentralized protocol in a sense, right? So by choreography, people were just saying that they're not doing orchestration. Orchestration, for people not familiar with it, basically means that you are coordinating a bunch of services from a central coordinator. So you have this single point of failure. That's why sometimes people don't like it. And you might want to use choreography instead. A choreography is like a pattern, you might say, or a practice where all these services, they coordinate with each other in a distributed way instead of relying on a central coordinator. So each one does the part that they're supposed to do. They don't have the entire view over the whole system like the orchestrator. Now, doing this is very tricky, and that's where multi-party session types and choreographic programming come in, using either verification or the high-level programming language approach. And then we have a choreographic programming language. And people lately have been also discussing, what does distinguish a choreographic language from a choreographic programming language? It's the usual problem. What distinguishes a language in general from a programming language? I stay out of this. I think it's a very big discussion that sometimes it's not very fruitful. But a choreographic programming language is essentially a programming language for writing choreographic programs. So programs are choreographies in a choreographic programming language. And that's the distinction. As to whether I coined the term, I do think so. I don't recall the term being used before. And actually, I met quite some resistance when I introduced the term. I met resistance when I showed the law of independent communications that I talked about before, because some people do not like out of order execution. That's essentially what it is. Although now it's pretty widely accepted. After all, I mean, even in Java or with modern CPUs, if you write two assignments in sequence and they are at different variables that are independent, they might be executed in parallel, or out of order. And here we have the same thing. But there was also some resistance to the name choreographic programming and the practice of, programming distributed systems like this, in a sense. I remember getting a review once that basically said, I doubt this can ever be implemented, right? So that's why I had to implement it in my PhD, because there were some people apparently who were doubting that this could ever work, even though the theory was already fleshed out, in a sense.
Mm-hmm. So Pedro, as our usually I'm the representative of the person who's kind of an outsider, but I think now in today's episode, Pedro is more of the outsider. How are we doing in terms of, for our listeners who are unfamiliar with choreographic programming? I feel like we might have been at a quite high level of abstraction, and we might need to get more concrete.
I think I'm being able to follow fairly well. One thing that I would be curious to speak about, to hear about is, okay. So you finish your PhD and then you got some resistance with anything that is kind of new. I feel it's always like that in academia. Like these people are already doing whatever they are doing, and I think it's kind of part of human nature to be a little skeptical that this new thing is gonna work, right? So you have to go there and show them and to prove how this all fits in and do all those Curry Howard isomorphisms and show how all of this are tied well together. And then you could like really show, hey, choreography is a really good idea. Is that when now you started, where does your book come in this story? When did you feel, okay, this is such a higher level idea that I should actually sit down and tell the whole story to a higher
Well,
audience?
first of all, I would really be remiss if I didn't say that even though I encountered a lot of skepticism, and it was much stronger than the support for a while, the people who supported my career in choreographic programming a lot, in addition to the people at the University of Bologna in the beginning, from the process calculi community, later on, they were the people who devised multi-party session types. To them, this was very intuitive, right? They saw that this would be a cool idea as well, and that we could both benefit from each other, right? These two topics, not us personally.
Right.
So, I mean, I was supported a lot by my PhD supervisor, Marco Carbone, who was really into this idea of let's try to develop this further, because they actually had these ideas before multi-party session types of using the Alice and Bob notation to model these more refined and specific descriptions of protocols for web services. And then Kohei Honda, the other author of multi-party session types and the original author of session types, and Nobuko Yoshida, who was the other author. So they supported me a lot. At least I felt like they were very accepting, and Nobuko in particular as well. Even after my PhD, she was always very positive. And in fact, after I found together with Marco and Carton Schurman at the university where I did my PhD, the correspondence between choreographies, choreographic programs, and cut reductions in linear logic, Nobuko contacted me and the others, and she was like, okay, but if you have figured that out, how far are we really from a Carry-Howard correspondence for multi-party session types, which is still missing? And I was like, I think we're very near. Let me try. We did it in 3 weeks. It was a real low-hanging fruit, because
Nice.
the underlying structures are so similar in a sense. So for the people interested in linear logic listening, you probably know about duality. That's the compatibility between two different propositions in linear logic. When you go to the Carry-Howard for multi-party session types, what you gotta do is to generalize duality from a binary relation to an n-ary relation, because now you have multiple processes potentially participating in the protocol. So we have a new inference system that is a strict generalization of duality. So in the degenerate case of two propositions, you get exactly duality. But otherwise, you get compatibility for multiple propositions. And what this means is that these theorems that you are composing, they can now interact bit by bit with one another following this protocol, in a sense. End of parenthesis for the people familiar with linear logic. So there were really a lot of interactions. By the time I started my appointment at the University of Southern Denmark, I was given a lot of freedom in what I would teach to master students. And I decided initially to teach microservice programming. And I'm really glad I did, because these people had, a lot of these people had fantastic careers afterwards, because they were among the early learners of microservices in Denmark. And then I switched to teaching concurrency theory with a twist. Usually people teach concurrency theory starting from process calculi and processes. I started doing the opposite. I started teaching people first choreographies, because that's our intention. That's the representation of our intention. So let's start by clarifying what protocols are, and let's make them clear. And then I explain processes and process calculi as a way to represent implementations of these protocols, right? I taught this for a few years, and I saw that people really liked it. It was one of the most followed master courses at our department. And after a while, I started making lecture notes. I was very inspired by the course by Frank Fenning in linear logic. He makes really beautiful
Right.
lecture
Yes.
notes, I must say. I love them.
Yes.
So I followed also kind of the same style in the beginning of the book. There's an example with a graph that represents flight connections inspired by one of his examples. And after a while, the lecture notes grew to be a book. Something really interesting that happened is that in the last 2 or 3 years when I was writing the book, we started a Koch mechanization of the foundational theory of choreographic programming. And at some point, we got stuck. We got stuck because it was really complicated to prove a lot of results about a structural equivalence that I had in the language. Now, I was encountering the same problem while teaching. That was the hardest part for my students to grok, all these equivalencies that you had baked into the semantics in order to actually be able to model the execution of a choreography. And so I decided to switch. And well, this was actually before seeing the problems with the formalization. I was seeing the problems in the teaching, right? So I decided to switch to a labeled transition system. And now I know that many listeners are not going to be familiar maybe with the labeled transition system, but I'm going to, so maybe I should explain it a bit. Yeah. So most of you are probably familiar with reduction semantics. Which basically works like this. You have some terms and you pattern match on these terms. So like if you have an abstraction in lambda calculus and then you have an argument that you're applying, then you replace the body of in the body of the function, you replace the name that you are abstracting with the argument. Now I'm saying this rule does a sort of pattern matching because it requires you to look at the structure of that you have an application and that you actually have an abstraction in the first component of the application. So you're looking a bit deep inside of the terms. In labeled transition systems, you basically do the same stuff. However, you have two big differences. One is a technical difference that you must always have. The other is a bit of a best practice, one might say. So the first one is that now reductions are labeled. The relation that tells you the small steps that you have in the semantics is not anymore just from terms to terms, but it is labeled by an action. So you can see that if you start from this term, you make a transition to this other term by making an action that is described by the label on top of the arrow.
In classic Italian style, Fabrizio is explaining with his hands. For the listeners, he is gesturing that there is, for example, an M, an arrow, and above that arrow there might be like a label alpha, and at the other end of the arrow is an M prime. So this is a transition from M to M prime with
Thank
the
you,
label alpha.
Also, it's getting quite late here, so I don't guarantee any quality to my explanations from now on this complicated stuff. Okay.
I'm following.
Another thing is a best practice now. Now that you have this, you can define semantics in a new exciting way, which is what people in concurrency theory know very well, but it's a trick that a lot of other people in programming languages do not know. So I hope that now more people will know about this after this podcast episode. Now, suppose you want to give the semantics of a couple of concurrent programs. You can do it in two ways. Here is the boring way. You write a rule where you pattern match and see that one program is doing a send parallel, and then you have another program in parallel that is doing the corresponding receive. And now, in the result of the transition, you have made them interact. Okay? That's one way. It's perfectly okay, but now I'm going to suggest another way that is, in some cases, much more interesting. So say instead that you want to define the semantics of a term in isolation. So you're not looking at how they're composed at all. You define instead the semantics of a program that is trying to do a send. So a program that is trying to do a send, you make a transition rule for that just consumes the send term. You go to the continuation. And in the label, you register that you are making a send. So the label says, hey, I am doing this transition by performing this send action. You do the same for receive. So now you have that the rule for receive is if you have a receive term, you just consume it, and you can always do that. And the label says, I'm doing that by performing this receive. And now you have another rule that says when you have a process and you don't care about the internal structure of the process. So you have this term doing a send. You can see it just from the label. So the term T goes to term T prime, and the label is a send. And then you have another term, T double prime, making a receive that corresponds to the send in the label, and it goes to T triple prime. Now in the conclusion, you can make these two terms interact. The beauty of this is that you have not looked at the internal structure of the terms. And if you make the rules like I told you just now for the send and receive, you can beautifully reason about the program equivalence of a process that is just trying to do a send, which you would have not been able to do before with the pattern matching. Because the rule that I told you for the pattern matching required to give meaning to a program, it required both the sender and the receiver. So you can only reason about what this composition is doing by looking only at the transition relation. Instead, with the second version, I have a semantics for a program that is just trying to do a send. I don't need the counterpart. So I can reason more structurally about the semantics of a program in its smaller atomic terms, in a sense. This is what enabled the concurrency theory community to come up with all the beautiful results they have about bisimilarity and other program equivalences that otherwise I doubt would have been possible. Thus, this simple trick will give you 1,000 papers, a headline for a blog entry. So, and this is what many people call the structural operation semantics approach, although both versions could be called under this, but this is what a lot of people mean by it. So anyway, if you use a label transition system and you use these labels to observe what your subterms are doing, you don't need a structural congruence anymore. You don't need structural equivalence to reorder your terms such that you can pattern match, because now they have the shape that you need for your rule to be applied. You can just look at the transition labels that they emit on top of this transition arrow and then define rules in terms of that. So you do not need the structural equivalence anymore, and I could finally totally remove it from my lecture notes, giving a much simpler theory, right? So my students now grokked it.
Could you also
Yes,
finish the
I
calc
went and
formalization
proposed to my
using that?
co-authors, hey, why don't we use the same trick? And after a while, they were like, initially they had to discard like 500 lines of code or something like that. I don't remember exactly. So they were a bit reluctant in the beginning. We have proven so much already.
Right. Yes.
But after a while,
Yes.
they came up with a really elegant way of following this approach. And then again, we had a lot of cross-fertilization because then by participating in the formalization, I learned so much about some of the details behind making these choices.
Nice.
So it was one of the very few moments in my life where I don't know if I would have gone down this way if I hadn't been teaching, right? So it was
yes.
it was a very nice moment. It felt nice that I could join these interests, the cut across, simplifying the foundations, teaching well to students, and making a mechanization out of it, right?
That is beautiful. That is very nice. Yes, Dan?
Well, I was going to say maybe in this last half hour we can. It's a good point to pivot into the kind of implementation section out of this theory area and talk about like what do choreographic programming languages now today look like in practice. And I think that they're speaking of what gets people interested in a topic. People got really interested in choreographies as soon as they figured out they could add them to their favorite programming language. So maybe we could talk about how that came about.
When I made the first implementation of a programming language, and I was working with Marco Carbone at the time during my PhD. It's called Core, and that's where it started from, essentially. I made a language that looked like Alice and Bob's security protocol notation, so it was easy to understand, but it was totally alien to any mainstream programming or programmer. It was very different from any mainstream programming language, right? And to add fuel to the fire, I compiled this to the Jolie Programming Language, which is, to most people, totally esoteric, right? So excellent as a first prototype, but very bad to prove to people that you can adopt this in the mainstream, in essence. At some point, now for a long time, during my tenure here at SDU, I was looking for funding to start a huge effort in bringing choreographic programming to fruition, in a sense. And through these efforts, I was able to hire two postdocs, Saverio Giallorenzo and Marco Peressotti. And they They are really great people. I mean, not only are they really fun to be with, but they are also great at doing research. And I started kind of thinking, what do I do with all this talent? What can we make? I mean, I'm just half kidding. What I did was I managed to convince them to start a Herculean effort into basically trying to rethink how we can make a choreographic programming language that didn't build on top of esoteric abstractions like Alice and Bob notation, but it was instead completely constructed on top of mainstream abstractions like functions and objects. It took us a while. The result is called the Choral Programming Language, which I think was a real game changer in the topic of choreographic programming. So the idea is very simple. Take Java, and classes and objects. Well, in Java, you have these data types. You just annotate data types with what we call roles or locations, if you like. So you instead of having an object located at a single place, which is what you have in Java implicitly, it's your computer, you can say that this object is distributed over Alice and Bob. It means that part of the behavior of this object is implemented by Alice and part of the behavior of this object is implemented by Bob. Now, what this allowed us to write is the signature of a very interesting method that we usually call com for communication. The method com takes data of any type at A and returns data of the same type at another location B. So it's essentially the signature of a function, if you like to think about it in terms of functional programming. And that's indeed how we discovered the choreographic lambda calculus, which is essentially the foundational theory behind all of this. It's a function that, given data of type T at A, then returns data of type T at B. And if you follow the contract we have, it's the same data, hopefully. Otherwise, you're not implementing communication very correctly or correctly. So this was a really huge effort. We reached this very simple realization, in a sense, after working really for a long time. And implementing this required implementing our own parser for essentially what is an extension of Java. So we have re-implemented the parser for Java plus these location annotations for data types, a type checker for it, and the compiler that, given this code, generates pure Java code that you can actually run, which is essentially a library that implements the behavior you wrote in the choreographic program for each participant. So you get a library for each participant, and now you have that if each program, you can just put this library in its respective program. If you run all the programs together, they communicate correctly as intended in the source choreography. So it's an extremely simple addition to a mainstream abstraction, that of a function or of an object method, that can already give you choreographic programming, in a sense. And this was a game changer for a couple of reasons. One, we wrote about in the paper where we introduced Choral, which is that now that we have reinvented the choreographies in an object-oriented language, we can have higher order choreographies. So, a choreographic method can take an object as a parameter that's only normal in Java, and that object is a choreography, again, because maybe it's located at multiple places, right? So you can have protocols parameterized on other protocols. And this is what people use a lot in industry. Like sometimes when you connect to a wireless, to a Wi-Fi network, there's a protocol that first allows you to select which kind of authentication method you want to use, and then you follow that. This is a list of protocols that you completely abstract from, as long as they respect some type signature that they perform, that they return yes or no, essentially, authenticated or not. You can have method overloading based on locations. That I found really fascinating. So you can write a class that has methods with the same name, but they behave differently depending on the location where you invoke them at. And that is completely new. We have subtyping for choreography. So you can define the type of a protocol. For example, I want to implement a protocol that, given data at A and at B, returns a result at C that then gets to another place and stuff like that. And you can write an implementation simply by writing a class that implements this interface, right? Because it's just a Java interface. So all these features, they just came together. So there was a real huge boost in features by combining or reconstructing rather choreographies on top of mainstream abstractions. We got all of the features of mainstream languages in a sense, or at least those of Java. And the other reason for which I think this was a game changer is that it showed that um, that building choreographic programming can be done with abstractions that people know very well in the programming languages community. So we broke out of the shell of concurrency theory, and now people who knew about lambda calculus could understand and do choreographic programming. It's just what some people call hybrid logic. You annotate, well, at least the propositions look like in hybrid logic. It's like a modal logic where every proposition is annotated with the world where it lives at, right? So
Right.
I think we don't
Yes.
have a propositions as types correspondence for this way of writing choreographic programs, but if I had to bet some money, I would say that we or some other people are going to find one by exploring the link to hybrid logic, maybe with a few different inference rules to adjust for how we compose these communications together. And what came out of that is that the community got larger. We met people who started mechanizing higher order choreographic languages. We met people that Andrew Hirsch, for example. We met other people who started doing logics for reasoning about transactional properties of choreographies, like in the Netherlands, the Shungshik Youngmans and colleagues. And Lindsay Cooper in the US as well. She started doing, together with her group and colleagues, what they call library level choreographic programming, where they encode these ideas as a library in types in Haskell, for example, or in Rust, or in other languages that are powerful enough to capture these concepts via encodings. And then you have choreographic programming as a library, as a domain-specific language, in a sense, an embedded domain-specific language in a mainstream language. So now you have all the tooling at your disposal, and you don't have to re-implement the entire parser like Marco Saverio and Fabrizio had to do for Coral. Mostly Marco Saverio.
So you also have going forward into the same question. So you worked with implementing these ideas in Java, in Haskell with Haskell, and these other like Rust apparently too. Then have mentioned that you also have consulted with some companies in industry. How did that relationship go
So
as
yeah,
well?
well, as I said at the beginning, I had professional experience before starting my studies, right? I've always felt connected to that. Indeed, after we created Jolie, Claudio Guidi and I, we immediately created a company for applying Jolie in the industry, in a sense. And so we still develop software. I still contribute to the scientific direction of how research and the development of Jolie and now also of choreographies can contribute to simplifying the development of these systems. Because there's a strong need right now in the industry for monitoring and understanding and managing the complexity, I would say. That's maybe the most important part of these huge distributed systems they're making. Microservices and service-oriented computing have popularized and maybe democratized in a sense or made more accessible the programming of these big distributed systems. So now suddenly you have people who are not really experts. They don't have a PhD in distributed protocols, and they hack together these distributed systems that collaborate in order to implement some web services or web apps or smartphone applications. Maybe they're making some backends, and now they're suddenly very complicated because they're distributed and they operate on a cloud. So I've been sometimes asked by companies when they have to deal with difficult decisions, like, "Hey Fabrizio, we gotta go to the cloud and understand what it means, understand why they want to do it and what they need it." Um, and now we're making this big distributed system, and we have one. This was one occurrence where they asked me for help. We have two consultancy companies that are offering us to do this for us, essentially. But they look very different, these solutions. Should we go for solution A or solution B, right? And when I looked technically at it, I could see that essentially what consultancy company A was offering them was a system with weak consistency and more speed, and the company B was offering them a system that was maybe a bit slower because it was implementing strong consistency, right? And I had to sit in front of a CEO who knew absolutely nothing about computer science, right? I had to explain what this means, what the difference is, and I had to understand from them, I had to extract from them what matters to them. You know, it turned out that they didn't care so much about speed. What they really cared about was consistency. It was absolutely essential to them because they were basing part of their business on it. So the choice was trivial. But I had this mediation role in a sense, and they were very happy for it. So sometimes it's a lot about translating things and trying to understand requirements from people who don't even know what
How hard was it? How long was that meeting you
I
were sitting
think it
with the
was
CEO?
about a couple of hours. But these are, I mean, these are
Wasn't too bad.
smart people. So if you try to actually bridge the gap to the kind of language that they're used to, or you try to explain to them what the 2 or 3 new words that maybe they didn't know about actually mean, then you can get really, really far. And that's how, in my experience, you build a lot of good relationships. Because there's nothing more than people hate sometimes, where the new smug person comes in and tries to drown them in buzzwords, because they can kind of smell it.
Yes.
They're not idiots. And
Yes,
they know their own
exactly.
buzzwords. They could
Yeah,
drown
exactly.
you into their buzzwords. So uh, that
Yeah.
was a very good experience. Some other times it's much more technical. I've been, for example, in touch sometimes with the people making Ballerina, the WSO2, the company making this other programming language for integrating services, because they were interested in some of the process calculi features we have in Jolie. uh, Sometimes we have people, especially from Italy, sometimes from Denmark, because those are my connections, sometimes regarding this stuff, where they need to make a new big software architecture, and and they would really like to be smart about, for instance, can we document at least the protocols we are using? And then maybe we have a conversation about that, about how you can use a choreographic language to write your protocols in a formal way. And then maybe you can hope to use that to actually monitor that your system does what it's supposed to do, because now you do have a precise, unambiguous formal description of it, instead of a wall of text in an inscrutable description that is 100 pages long, right? So I think a lot of it is about thinking about features that might come in handy to reduce complexity. And that's what a lot of people need in microservices, I think, because the languages that we have in the mainstream are getting more and more complex in a sense. And now we are piling on top of it all these architectural ideas and patterns that people have for distributed systems and distributed applications. And sometimes doing the mapping is very complicated, because the code, some people would say, does not make your intentions manifest. The architecture is not manifest. It's hard to see from the code that you actually wrote, from the syntax of the language you used. So I try to help a lot with that, essentially.
That gives me kind of an impression of what are the short-term kind of goals. I think that industry kind of needs languages that maybe make their intentions more manifest. That's what you were talking about. What do you think, like, in 10, 15 years, 20 years, um, distributed programming would look like? And I mean, that's considering also, we've been focusing on choreographic programming, but there's been other paradigms as well that are kind of targeting that area. So what do you think are kind of, I don't know, long term, what do you think is the vision there? And do you think that there's, I don't know, do you think that functional programming plays a role? Do you think that verification plays a role, type systems?
Well, I think
What
everything
is
plays a
that going
role
to
in a
look like?
sense, also because we're always going to be full of legacy code that we will need to integrate somehow, right? So a lot of people are still writing code in C. In some cases, it's even appropriate to still write code in C, right? But that's a very good question. Let me introduce a bit of motivation behind also why we are doing all of this. if we're thinking about what we are using today in terms of services from the government, from companies, etc., these are distributed systems. We interact with distributed systems on a daily basis. And these have become essential. It would be hard to replace them nowadays, so their use is just increasing. I believe, and I observe at least, that many programmers, when they're faced with understanding distributed code, they make blatant mistakes. It's really hard to understand distributed code. It's hard to write, and it's even harder to read, right? Even experts make a lot of mistakes that we know empirically. The fact that we find the distributed system code hard to understand means that it is even harder to explain it to others. So we end up in a society where we, the people who are supposed to be the experts, they can't even explain well to society what the hell these systems are doing. But these systems manage the people's data. They manage their insurances. They manage a lot of stuff, right? So we can't, of course, fix everything from the wonderful tower of choreographic programming. There are a lot of subcomponents in the systems, including AI nowadays, that we also need to look at. However, I am baffled by the fact that we are not yet in a place where we at least can tell people what kind of communication flows are implemented. These are totally inscrutable. In fact, they are so complicated that a lot of people who make programming frameworks for distributed systems, they try to hide it from the programmer, actually, where data goes. I think we should know where data goes. I think it's our duty to know where the hell the data goes, because we need to tell people where the data goes. Otherwise, they will never be able to engage and get actionable information that allows them to choose between service provider A or service provider B, because they should also choose based on what they understand about how service A uses their data, who they communicate it to, and how it's used over there, and instead how service B does it together with its third parties. So for me, the long term looks like we should know, and hopefully we will know, and hopefully we can even explain to the average user where data goes when we write programs, how it's manipulated, and what kind of important information it contains. At the very least, we owe people that. And that's why I would like to work towards there. At the same time, I think an intermediate step is to make this much easier for industry. I mean, industry is not doing this. Instead, we get these wonderful, inscrutable cookie texts that we know very well from social science, don't work very well. But to be honest and to be fair to them, sometimes it's just too hard. You have some people who change a little bit of the distributed system. These are programmers. They just add a new feature. Now the data goes also to yet another place. So it's very hard for the people who write these cookie texts, for example, or whatever information about the website, to actually know what the system is doing. So first we got to fix this. And if we want to fix this, it needs to come with a productivity advantage. So it needs to be easier to do that than to do the old stuff. And that's why I think choreographic programming is interesting, because it is actually simpler, it takes less time, it has less side effects, and it just has a simpler architecture. So it's simpler to write a choreography instead of writing manually the code that you get out of compiling a choreography, right? Which is the usual distributed application. So that's the angle there. And then hopefully out of this, since in a choreographic language makes syntactically manifest what communications are going on, then from there we can build tools that aid people in declaring what is happening to user data. Or, also if you think about cybersecurity, we have huge supply chains where a company depends on another company that depends on another company, et cetera, et cetera, et cetera. We kind of need to be better at ensuring that these digital supply chains actually work. The people who devise those are not the people who think about how to write the next distributed agreement protocol. These are super experts. The people who implement these supply chains are maybe software engineers who didn't even get a course and they don't even know what distributed agreement means, right? So we need to make it easy enough for them. We need to make it a bachelor level stuff at the very least to write a distributed system that works very well and is understandable.
I think this is an amazing, amazing place to wrap up this episode, because now you just gave a really good spiel why you believe that choreographic programming is the next step. Like, we're really trying to make things simpler here, and this will come to gain for literally everyone. Because in my point of view, not only my point of view, my experience is that distributed systems and concurrency is hard as fuck. This stuff is hard because our minds are not made to think about things in parallel. My mind works in like, okay, I have this one thing that will happen, that other thing, and then that other thing. It completely forgets that there's the whole universe is happening simultaneously at the same time, right? So when you sit down and actually try to program that stuff, then you have to keep track of this stuff happening here and this other stuff happening here and how they're communicating. It's hard. It's extremely hard, and having this certainty, in my point of view, and where I am sitting in, that there's some really smart people like you, and that is very passionate to make it simpler for people like me to understand, really makes me feel a lot better. Is there any final remarks or anything in this episode that you think would be important to bring about and we didn't have the
I
opportunity
think actually you
before we
made
wrap it up?
a very nice final remark. It touches on what I usually do with students and at a lot of seminars. I first show people a distributed program,
Yes.
like with 3 processes interacting with one another, and I ask them, what are they doing? And and they get scared, like, oh, I actually have to apply myself, I will
Right.
have to
Exactly.
work to follow this seminar. And then I show them by drawing arrows that connect the send and receive actions at these programs. Look, I'm going to solve it for you. This the relation that connects, that orders all of these actions. Actually, you have an ordering to all the communications that are going to happen. Now, instead of having this scribble full of lines that connect all these actions. Why don't we just write it down as an orderly structure? And then I show the choreography and everybody can understand it because it's so intuitive. So the key principle of choreographic programming might be that what is simple, these communications, their ordering, should look simple. And that's why we're making a language for it, essentially. But yeah, that's exactly what we're doing.
I think a good place to wrap up, though, is, I mean, what are the limitations of choreographic programming right now? Like, what do you think it's not good at? And because, I mean, right now it sounds like it's already, everything's done and solved. Now all we have to do is, market it to the right CEO. What are the kind of small scale things, and what are things that people can start, looking
I
into?
love that you are so
Maybe.
scientifically correct. Then I'm not so sure closing on a low is exactly the best place, to have final remarks.
All right.
But I'm
Yeah.
just
Yeah.
joking. I
Editor,
actually
please
think it's
cut it
excellent.
out.
So the thing is, choreographic programming poses a new challenge. When you write distributed code, you can basically implement whatever concurrent pattern you want. You just need to string together and compose in parallel the right sequences of send and receive actions, basically. Put inside of the right conditionals or non-deterministic choices and stuff like that. However, in choreographies, we have a harder job. We actually need to come up with syntactic abstractions that describe these patterns. So for a long time, for example, we didn't know how to do properly producers consumers in choreographies because non-determinism is a bit hard to capture when you have this Alice and Bob notation. Um, so I would say that the big hurdle in developing choreographic programming is that what came easily in the semantics of process calculi or concurrent lambda calculus, so these patterns that you can observe during the execution of these programs, they arise from the semantics of these languages. Well, these semantics, we actually now need to transform it into syntax. And giving an orderly, structured syntax to all of these possible patterns, well, it requires you to be able to imagine what all the possible patterns that you have in distributed protocols might be, right? Which is hard. So every year, I think there's some progress made on that in understanding, oh, that's another very useful concurrent pattern. We should have new syntax to capture it, or we have a proof that you can capture it with the old syntax. That's one part of it. And another big part then is to make the compiler of a choreographic programming language smart enough to produce a correct implementation of these new syntactic abstractions that we have devised, right? So that's why it's taking a bit of time. I think that recently, since the community is getting bigger, progress has become much faster. So now I see regularly at top conferences, at least for the past 3 years. There's not a top conference without a choreographic, well, at least there's always some choreographic programming papers distributed over the top conferences in programming languages or concurrency. So there are a lot of new results published regularly now. I think what we need to do now, and it's part of a big project we're running here now in our group, is to systematize this. We need to find a mathematical framework to actually reason about the expressivity of a choreographic programming language and try to establish separation results. Like if you have a language designed like this, then you cannot express this entire class of protocols. We need to be able to start stating stuff like that in order to guide in a bit more organized way the development of all these different choreographic programming languages, because it's starting to be like process calculi. Every year people would make 10 or 20 new process calculi to capture this feature or the other. And I would like to avoid that for choreographic programming, if at all possible, or at least restrain it a little bit, or at least provide some guidelines for it.
Yeah, it's totally ridiculous time for me to have brought up that question. Maybe we will like shuffle it around in post or something like that. But I think that it is important to kind of emphasize like this isn't a solved area. This is actually quite an interesting and exciting thing to be working on.
It's also very nice for the listener. You know, a lot of our listeners are interested in this field, and maybe they might be interested in pursuing a master's or a PhD, and maybe they can come to your university and be your student now that you gave this amazing spiel for them. So now that we understand what are the kind of problems that I've been working over there. So with that out of the way, but thanks, Dan, for that question. It was actually a pretty good question that I totally forgot. So it was actually pretty good. But well, it was an amazing pleasure to have you guys here today. It was very nice meeting you, someone who can match our Brazilian sarcasm level. I had so much fun with you. I hope that we can meet in one of these conferences one day. Thank you so much for your presence.
It's been a real pleasure, and I had a lot of fun too. Thank you.
Thank you, and thank you, Dan, for co-hosting here. You basically came up with the whole structure of this interview. So thank you so much for that, dude. Oh man, this conversation with Fabrizio was so funny. We had so much fun. He's so sarcastic. And I sure learned a lot. You know, distributed systems is not my exact field. I studied very little of distributed systems, of concurrency. So I really had to put a lot of effort into keeping up with all these things. I hope you guys learned and enjoyed this episode as much as I did. If you guys have any questions, any comments or any remarks, please send us an email, typetheoryforall@gmail.com. I know I still suck. I still haven't got a .com email. I will do it eventually, I swear. Don't forget to also follow us on Twitter @TT4All. We are also running a study group on the Software Foundation through our Discord. So if you think that's something you would be interested in, there is still time to join. Go to our website, typetheoryforall.com, and join the Discord channel to be part of that. Finally, as soon as this episode is released, I will be doing a Euro trip. I will be visiting a couple of places in Europe. I'll be participating in ICFP in Milan. I'll be in some summer schools in Birmingham, in Fischbachau. I'll visit a couple of universities in Gothenburg, Amsterdam, Rotterdam, and Paris. So if you guys live in any of those places, please reach out. Make sure to follow us on Twitter to know where I'll be at. For those who are my listeners and I'm able to meet with them, I have a very special gift. I have been making these really cool t-shirts that I want to give away in these events. So if you're a listener, you live in Europe or you'll be in Europe as well, please reach out, send me an email, or reach me on Twitter. There is also my personal Twitter that we can speak, or Discord, and I'll make sure to save a really cool t-shirt for you. Now let's catch some specials.
It's always a pleasure. I hope one day to be nearly maybe half as famous for my actual research as I am for being a podcast co-host. Maybe that dream will never come true.
Dude,
but,
it doesn't matter. Fame is fame. You just take it.
Yeah.
Then
people will run up to me at conferences and say, oh my gosh, it's you. I'm like, do you know anything about me? No. I know your voice. It's creepy to see your face.
Then you know what? You had it coming. You know? Do you know Pedro what Dan did when he met me once? We were at the meeting and then was like, so then knew me because of choreographic programming, and then we were talking, and he went like, "Oh yeah," and then I know you also do this Jolie thing, but it's kind of like your hobby, right? You do it in your. And I was like, "What the heck?" And you know the Jolie, since all these primitives we made, it came up by coincidence that they are in a correspondence with concepts that they have in meta models for domain-specific languages to define software architectures in software engineering. Like they were coming up with very similar primitives, just not for programming languages, but only for describing software architectures. And so in the software engineering community that works with that, I do Jolie as my main thing, right? And then I do some other obscure types and logic and programming languages stuff that God knows what it is. But Fabrizio does Jolie. He's cool. and then I have the when we started doing this mainstream choreographic programming, implementing all sorts of stuff. I think I became weird to the concurrency theory community too. Although I haven't asked. I'm afraid to ask at this point. I'm weird to freaking everybody.
So you still decided.
And to your kids, you're just mostly a guy who makes the sandwiches, and I don't know. He goes away while I'm at school.
Exactly right.
No, what surprises me the most is that even after all of that, you still hired him.
After I insulted,
right?
I think I don't remember, but I think he did it right after I hired him.
Smart.
He was quite the evil mastermind there. I was like, damn! I just gave him a very long contract, and now I'm stuck with this guy. No, that's amazing, Pedro. I mean, then. Then why are you brilliant again? You have to remind me.
That's what I was gonna say. Like, you even lost your words.
No, that is great. I mean, he goes around. Imagine he goes around at conferences saying, Fabrizio has generously hired me while I work also from the US and whatever. And I'm there like dumbfounded. Like, I'm so lucky to have him. And he's also making me look good because he goes around telling that I'm the generous person and he's the lucky one, you know? Fantastic.
Okay, I'm going to hit stop real quick here.